In this segment, I want to explain how systems of ordinary differential equations can be decoupled and solved by means of expansions onto the set of eigenvectors of the matrix in the system. So we have in mind equations of the following form: x dot is equal to ax, where for each time x is a column vector with n components, and the matrix A is real and n by n. And decoupling is the idea that we would write the unknown vector x by means of its components in the basis of eigenvectors of A, provided this basis exists. And so we'll write x of t is equal to some matrix V times coefficients y of t. And we'll assume throughout that the matrix A has n eigenvectors. It means that the matrix V has columns v1 through vn, which themselves are eigenvectors of the matrix A. And so in matrix form, if we apply A to V, we get back V up to a diagonal matrix, which contains the eigenvalues on the diagonal. So lambda 1 through lambda n here, and the other elements in D are zeros. And so then if we realize this this matrix vector product here, and write it in components, we'll have that x of t will be the sum for j running from 1 to n of yj of t times vj. In other words, you have a linear combination of the columns of the matrix V, and the yj provide this the coefficients in this combination, and it's only the yj that depend on time, not the vj. And so in terms of a picture, what happens here is that we have these eigenvectors at our disposal. So here let's say v1 and v2 in 2 dimensions, and they're not in general going to be orthogonal to one another. But if you're given some vector x here, what this operation that we've just written consists of is in decomposing this vector in terms of its components along v1 and v2. And so here's x, and here is what y1 v1 would look like, and here is where y2 v2 would be. And so by adding up these two components here in 2D, we would have the vector x. So those y's are the numbers needed so that these combinations work out and reproduce x at the end of the day. And so the assumption that A is diagonalizable here means that we are allowed to write this matrix here with as many eigenvectors as you have eigenvalues. There is no deficiency, and as a result of that, automatically, if you have the proper count of eigenvectors, it turns out that this matrix V will be invertible, and we'll be able to write A as V D V inverse. In other words, we now have a factorization of the matrix A, and it's often called diagonalization of the matrix A. So matrix A is diagonalizable. So A diagonalizable means here that V has the proper count of columns, is a square matrix, and is invertible. Okay, so let's return to the equation that we're trying to solve here, and the homogeneous equation x dot equals the x, homogeneous because it doesn't have a right-hand side. And let's see how that works when we start from this equation that we'll label 1 and try this decoupling strategy to solve it. So we go ahead and use this expression here, plug it in equation 1, and we end up having that v y dot of t is equal to a v y of t. That's when you use x equals vy. Then by means of the relationship that v are eigenvectors of A, we have this is equal to v times d times y of t. And now we have on the left and on the right v that multiplies the whole relationship that we can get rid of because it is assumed to be invertible, and we now have an equation for y of t. And this is exactly the kind of relationship that we now like and that we're going to call decoupled. If you look at it component by component and you realize this diagonal matrix vector product, you end up having yj dot of t is equal to lambda j yj of t, which is now a scalar equation, and that is now something that we know how to solve, and the solution we know is of the form of an exponential with an arbitrary multiplicative constant. So we have yj of t equals cj e to the lambda t as a solution of this equation. So solving for those components in the basis of eigenvectors is now doable because this decoupling occurred. So in other words, all these equations that were scramble or couple to one another, this undoes this scrambling and allows to solve. And so now that we have the components yj, we can go back to the expression of x as a function of y. I can go ahead and apply this relationship here to write it out explicitly, and we'll have that the solution x of t now will be the sum over j of these components yj that we've just obtained, so cj e to the lambda jt, and then that gets multiplied by the eigenvectors vj. So that is the solution of equation 1, the general solution with its arbitrary constants. We could stop here, but we want to formulate this solution in terms of now the basis of functions that solve the system of equations, and formulate this in terms of the fundamental matrix to have matrix expression. So it's going to be an equivalent way of formulating this expression that we've just obtained, but it's worth going through that. So let us remind ourselves that we have just obtained a basis of the vector space of solutions of the system of ODEs in the form of here exponentials of time that are scalar times vector that do not depend on time. And so this is the basis that we have just obtained. And sometimes for solving these systems of equations, one starts from this form and one says, let's imagine that we have a guess as to what the solution looks like, and we postulate that x of t, just pulling this formula out of a hat, would be of the form exponential lambda t times v. What would it take for this guess to provide a solution of the starting equation x dot equals ax, here labeled 1? And the answer would be that v would need to be an eigenvector of a with eigenvalue lambda. So you could start the process this way, postulate a guess of this form, and just end up directly at the formula for the basis here. So either way, here you have the basis, and a nice way to organize this collection is to put it as columns of a matrix that we then call the fundamental matrix for the system of differential equations. The fundamental matrix, we're going to call it capital X. And it's going to be a function of time. All its elements are going to be a function of time, and it's going to consist in placing those basis elements as columns of this matrix. So e to the lambda 1 tv1 to start with, and then e to the lambda 2 tv2, etc., all the way to e to the lambda n tvn. So this is going to be a fundamental matrix for the system that we started from. Expressed in this form, we can go back to this expression for the solution and write it in a slightly different form. We now have a matrix vector formula for it. We do no longer need the sigma notation, and we have x of t times the vector c of coefficients. That linear combination of the columns of x of t will reproduce the formula for x of t we just had a minute ago. Now, this fundamental matrix itself solves the ODE because this system needs to hold regardless of the coefficient c we have in this formula. Here, we see that x needs to obey x dot of t is equal to ax of t, because each of the columns of capital X of t needs to obey the system of ODEs. So that is the notion of fundamental matrix. Now, this x of t that we wrote is one possible such fundamental matrix. It is not unique. You may be able to come up with other fundamental matrices which have another basis as its columns and serve the same purpose of being able to write a general solution by means of linear combination of these basis elements. For instance, you could imagine that you would have the same solution x of t given in terms of another fundamental matrix x tilde of t and coefficients x tilde, c tilde that would correspond to that particular fundamental matrix. And a great example of such a fundamental matrix is what we call the matrix exponential. Denote it e to the ta, and this is a very specific operation. It does not consist in general in exponentiating the elements of the matrix entry-wise, but rather the matrix exponential is defined by means of the Taylor expansion evaluated with matrix terms in it. So it's going to be identity plus t times a plus t squared over 2a squared. plus t cubed a cubed over 3 factorial and so forth. So this expression converges and it gives us by definition the matrix exponential. There's a nice way to express this matrix exponential if we remember that A is decoupled by means of the basis of eigenvectors, and we write A equals VD V inverse, and we go ahead and see that each of the terms in the series like that also get decoupled by the same operation of changing basis into the basis of eigenvectors. And after some a bit of manipulations, we'll see that the matrix exponential in fact can be expressed when the matrix is diagonalizable as V e to the TD V inverse. In other words, it's decoupled by the same matrix V as all the powers of A. And I remind you, V is the matrix of eigenvectors, so V1 through Vn as its columns. And this matrix e to the TD now does have a simple expression because it is a diagonal matrix. The exponential just consists in exponentiating all the entries on the diagonal of it, and then you still have zeros outside of the diagonal. So this is another expression for another fundamental matrix, and it works equally well. It serves the same purpose as the one we previously wrote. So what's the relationship, you'll say, between capital X of t and capital X tilde of t? Why do we have two of those? Does it matter? Well, the first thing we can notice is that we can indeed write X tilde as a function of X. If we go ahead and consider the product here, V times e to the TD, and we write it out, we'll have a diagonal scaling of the columns of V by means of e to the TD, and we'll have this, e to the T1 V1, etc., e to the T lambda n Vn. That's the product of those two matrices. V inverse remains to the right of that. And what we are looking at here is precisely the old notion of capital X of t here equals to V e to the TD. So that is the relationship between those two fundamental matrices. And they both serve the same purpose. They both contain as their columns basis elements for the system of ODEs we started from. And how do we know that those are both valid fundamental matrices? Well, they both obey the equation. So x dot of t is equal to ax of t, and this is equally valid if you do that with x tilde. So no question about that. It does solve the system of ordinary differential equations. And on top of that, it allows us to fit any initial conditions that would be given to us. How would that work? If we want to use capital X, the first fundamental matrix, in order to fit initial conditions, we would do it as such. X of 0 is equal to capital X at time 0 applied to the vector C. And now you see there's a one-to-one relationship between the vector x of 0 and the vector of coefficient C. We can obtain C by solving this system here. And the statement that we have a fundamental matrix here includes the clause that this matrix should be invertible. So that is going to follow in the case that we've seen earlier, and in general it is true that this matrix here is invertible. So there's no question that this is going to be fine as long as the matrix A is diagonalizable. And we could do the same with x tilde, and we could find here again a way to handle the initial conditions by means of the other fundamental matrix for another set of coefficients C tilde. And something very special that happens for this choice of x tilde is that we are looking at the matrix exponential e to the 0a. And if we go ahead and remind ourselves what the matrix exponential is in terms of here this Taylor expansion, we'll see that if we plug in t equals 0, we recover the identity. So this is the identity. As a result, the expression for C tilde is rather simple. Here we have that it is going to be equal to x of 0. So that, I would say, is a redeeming value for the matrix exponential. Why consider a second fundamental matrix when we had the capital X of t that was perfectly valid to start with? It's because here the expression of the coefficients is particularly simple. So again, the contrast between these two fundamental systems here is that this is the expression for x, and x tilde, I remind you, is just this v e to the td v inverse. The difference between the two is the presence of this v inverse here that allowed us to have this nice expression for the coefficients in terms of the initial condition. All right, so this pretty much thoroughly solves the linear system x dot equals ax. And what I'd like to do, what I'd like to finish with is a quick run through of what happens if we have an inhomogeneous system. What if instead we were given this, the equation here that I'm going to label 2, and that is x dot of t is equal to a x of t plus a right hand side q of t. So again, here a vector with n components for each time, and it is real valued, and it's just some functions of t that we have as an inhomogeneity. Decoupling is still achieved by this transformation v, and that is what's going to allow us to have the solution also in the inhomogeneous case. So let's see how it works and try to draw a parallel with the simplifications we obtain in the homogeneous case and go through the same motions and see what the expressions become. So we have v y dot of t is equal to a v y of t plus q of t now in the inhomogeneous case. So this is still equal to v dy of t plus q of t. And so we can go ahead and invert the matrix V on the left and on the right, and we obtain y dot of t is equal to dy of t, and now we have to contend with the inverse of V applied to Q. And so now component-wise, we have that the jth component of this vector relationship would be yj dot of t is equal to lambda j yj of t plus the jth component of this vector V inverse Q. So here it is. At this point, it is a little more difficult to solve than the simple exponential solution that we had here in the homogeneous case. And the way to handle an equation like this is by this method called the variation of parameters. And the idea of that method is to go ahead and write that to have something that's quite analogous to what we had seen in the homogeneous case. What we are now going to seek is an expression for yj of t that involves a multiplicative function of time uj of t in place of the cj we had back in the homogeneous case. And then that gets to multiply e to the lambda jt. And so then now the game is how to determine this uj of t, and there is a whole segment on the method of variation of parameters that you can go ahead and take a look at to determine this missing function uj of t. And once that's done, then you can go ahead and form the solution in terms of these uj. Those will contain the arbitrary constants, but in a more complicated fashion than the CJs used to enter this expression here, and we'll end up having the sum over j running from 1 to n of uj of t e to the lambda jt times vj. So that provides the general solution in the inhomogeneous case once those uj functions are solved for. So now I have the opportunity to also show you what the method of variation of parameters gives us for systems with the formalism of the fundamental matrix, and this is something we can probably achieve here in this little space. And so the way to do that, and to have an expression that would be the matrix formulation of what we've just obtained here, is to go ahead and write this in terms of the fundamental matrix. I remind you, this basis elements here can be taken to be the columns of it. So what we're really doing here is to write x of t as the product of capital X of t, this fundamental matrix, times here now a vector u of t that will have as its components the uj. So this is exactly the matrix reformulation of the expression we had a minute ago. And now we go ahead and substitute that in our ordinary differential equation. So what happens then when we do that, in fact, let's make it clear what we're doing here. We're plugging this expression we just obtained into the equation 2 we started from here, now the inhomogeneous one. So let's do that. And what happens is this: we have x dot u plus x u dot is equal to a x u plus q. Now, because we know what x dot obeys, which is this one, we can get rid of this term and that term. They cancel out, and we are left with an expression for u dot. U dot is equal to x, and x is a function of time, so x of t inverse applied to q. And now we go ahead and integrate that in time, and we have the expression of the functions u that we were missing, and they're just the integral of x of t inverse times q of t dt. So it's the antiderivative here of this expression, and that's what the function u of t needs to be. Those will come with arbitrary constants. We go ahead and compute this integral when the x and the q are given to us, and then substitute it back in there, and that's a solution to the inhomogeneous system. So the last thing I'll mention is that the idea of inverting for each time this matrix X does not have to be as scary as it looks. In fact, this operation is actually quite nice when we have the choices of the fundamental matrix like those ones that we saw. For instance, if we start with x of t is equal to v e to the td, which is what we have here, and we try to invert this relationship, then we can go ahead and invert factor by factor, because those are both invertible, and we go ahead and obtain that this is in fact exponential minus td. That's a nice property here of matrix exponentials or diagonal matrices. It's just minus t to invert when we want to get the inverse of capital X of t, and then times v inverse. And if on the other hand we had taken x tilde of t, the matrix exponential of A equals to v e to the td v inverse, then the inverse of that would have been rather simple. X tilde of t is just here. Let's go ahead and start with this expression. That's just v e to the minus td v inverse, which is nothing but exponential minus ta. That completely solves our systems, both the homogeneous and the inhomogeneous one.